Section 12.2, Calorimetry and Thermodynamics. So if you remember, in Section 12.1, we were focused on heat, and we really did one main equation, Q is equal to M times C times change in T. Now we're going to take that and we're going to start exploring heat in systems. And how do we study heat in systems? When we study heat in systems, we use a device called a calorimeter, which is essentially a device which retains heat. So it can capture how much heat is given off by a particular substance. All right, conservation of energy. When we talk about conservation of energy, it's the same thing as everything else conservation-wise. Conservation of mass, conservation of angular momentum. We've talked about earlier in the year. Energy is not created nor destroyed. It is simply changed. So that means when we have energy changes in a system, that means they're constant. Something that loses energy, if A loses energy, B must gain that energy. So a calorimeter is a device that helps us capture that energy. And it's insulated, so the heat loss to the outside environment is very minimal. And we will do a lab in which we make a very cheap calorimeter. And you guys in advanced chemistry have kind of worked with calorimeters before. You've worked with thermodynamics a little bit before. So some of the stuff you see in this section today will be pretty familiar to you. So we talked about calorimeters. All right. Here is our calorimeter equation, which is really big. We already talked about Q equals M times change in T. That's for one particular substance. But let's say I have a calorimeter equation of, I have water. It's at 30 degrees Celsius. I add 12 ice cubes with a mass of 0.1. What is the temperature of my water going to be? That would be an example of something that we're going to use the calorimeter equation for. And the calorimeter equation is the final temperature of the solution is equal to Ma times Ca times Ta. M being mass, C being specific heat, and T being temperature, plus Mb, Cb, Tb over MaCa plus Mb, Cb. So that is our calorimeter equation. And that is how we're going to kind of solve for if I add something cool to something hot, what's my final temperature going to be? Or if I add something warm to something cold, what's my temperature going to be? Or if I add two things that are lukewarm, what's my final temperature going to be? So when we take a calorimeter equation and we do a real life problem, and we look at a real life problem such as this, we have a calorimeter contains 0.5 kilograms of water at 15 degrees Celsius. A 0.04 kilogram block of zinc at 115 degrees is placed in the water. So we just placed a really hot block of zinc into our water. What's the final temperature of the system going to be? Well, let's look at this here. We have A and we have B. For our intensive purposes, A will be the water. So that a mass of A is 0.50. The specific heat of A, which will be located in your book in chapter 12, I think on like page 3, I want to say page 318. The specific heat of water is 4180, and the temperature of our temperature has to be in Kelvin. So C plus 273, 15 plus 273 is 288. Likewise for B, the mass of the block is 0.04. The specific heat of zinc, which is in your book again on page 318, is 388. And the temperature of zinc is C plus 273. Well, 115 plus 273 just happens to be 388. So if we take our calorimeter equation, TF is equal to Ma Ca Ta plus Mb Cb Tb over MaCa plus MbCb. We go ahead and we plug in our numbers. 0.50 times 4180 times 288 plus 0.04 times 388. That's the specific heat of zinc times 388. That's the temperature of zinc in this equation. Over our mass of water, 0.50. Specific heat of water, 4180, plus the mass of water, or sorry, the mass of zinc, 0.04 times the specific heat of zinc, 388. We go ahead and we do this, and we find out that the final temperature of this solution will be 288.7 degrees Kelvin, or 15.7 degrees Celsius. So you can see by adding a very small piece of zinc at a very hot temperature, it raised the water, but not a whole lot. It only raised it really 0.7 degrees. So that is a calorimetry equation. You will do an example of one of those later in the week when we do our calorimetry lab. Moving on, we have to talk about thermodynamics. What is thermodynamics? Thermodynamics is essentially the study of thermal energy, the study of heat. And when we talk about the study of heat, we're going to talk about phase changes. What happens with phase changes? Well, you can have things melt, you can have things boil, you can have things freeze, you can have things condense, you can have things sublime. All of those require energy. Anytime you have a phase change, it requires energy. So a melting point is which something goes a solid to a liquid. The amount of heat required for something to melt is called the heat of fusion. The heat needed to melt a solid is called the heat of fusion. Now the heat of fusion is also going to be in your book. It's a constant. It varies for every single compound. So water has a different HF than methane. Methane has a different HF than zinc. Every compound is going to have a different heat of fusion. So a heat of fusion is the heat needed to melt a solid. And that equation, Q, is equal to M times HF. M being your mass of how much you have, and HF being the heat of fusion, which is a constant depending on your substance. Likewise, we said it takes heat. Oh, sorry, skipped one thing here. If it freezes, it's going to be a negative value. If it freezes, you'll be going backwards and it'll have a negative value because you're removing heat rather than adding heat. So heat of fusion is for a phase change when we're going from a solid to a liquid or a liquid to a solid. What happens if we're going from a liquid to a gas or gas to a liquid? Well, then we're dealing with the boiling point. The boiling point is the temperature at which a liquid becomes a gas. That is heat of vaporization. So when we talk about heat of vaporization, we are talking about the boiling point, liquid to a gas. And remember, it's the heat required to evaporate. Anytime you go through a phase change, it requires heat to transfer that from a liquid to a gas, or a liquid to a solid, or solid to a liquid, or vice versa. So when we do that, same equation, Q is equal to M times HV. These HV values can be found in your textbook. And when we do that, if it condenses, Q is equal to negative M times HF. So we take these and we're going to have two separate problems. First one is a fairly simple problem. If 5.00 times 10 to the third joules is added at 273 degrees Kelvin, how much ice is melted? Well, it gives us two pieces, really one piece of information. Q is equal to 5.00 times 10 to the third. We're looking for mass, and since we are melting our object, we are dealing with HF. And it's the HF of ice, or the HF of water. And the HF of water is 3.34 times 10 to the fifth. So we go ahead and set this up. Q is equal to M times HF. Q, 5.00 times 10 to the third, is equal to M times HF, and HF is 3.34 times 10 to the fifth. We divide by 3.34 times 10 to the fifth. And our final answer, our mass, with sig figs, because we have 3 sig figs, ends up being 0.0150 kilograms. Not a lot of ice. That's only 15 grams of ice, which would be the weight of about probably 1 ice cube. So that's our first example with our transfer of heat. Our second example is now we're taking a phase change plus we are adding heat to the equation. How much heat must be transferred to 100 grams of ice at 0 degrees Celsius until the ice melts and the temperature of the resulting water is 20 degrees Celsius? What I'm going to do here is I'm going to draw kind of a downward arrow. All right. We're starting at 0 degrees and we're going to 20. However, at 0 degrees, since we are dealing with water, we are going to have a phase change. So we need to figure out the heat required in the phase change. Well, that is going to be Q times HF. Then, once we get all the heat required to go from a solid to a liquid, our liquid is going to heat up from 0 to 20. And when we go 0 to 20, we're going to use Q is equal to M times C times change in T. If we figure both of these values, we can add them together, and that's the total heat required to take 100 grams of ice at 0 degrees, melt it, and then heat that water up to 20 degrees Celsius. So when we go ahead and plug in numbers, our mass is 0.100 times HF, which is 3.34 times 10 to the 5th. Add those together, or multiply those together, and we get 33,400 joules. And that's the amount of heat required to melt 100 grams of ice into water. Then, how much heat is it going to take to raise the temperature of the water 20 degrees? Well, our mass is 0.1, our specific heat of water is 4180, and our temperature change is 20 degrees. Multiply those together, you get 9,196. Add those together, you get 42,956 joules for the entire process. Now, if you're going to be specific, we have 3 sig figs, so it really should be 42,600 joules. So anytime you're doing a phase change, you have to figure out how much heat it requires to do the phase change first, and then on top of it, how much heat is put into that liquid or to that solid additionally. So we will do a couple of these examples in class to kind of help you out with it. So that is phase change. The last couple things that we have to talk about is the laws of thermodynamics. And the laws of thermodynamics, there are 3 laws for thermodynamics. First one, the total increase of thermal energy of a system is the sum of the work done on it and the heat added to it. Essentially, if you take an upper level physics course or chemistry course and you're going to have to study thermodynamics, you're going to have to study the work and heat put into a system, and that's the total increase of thermal energy, is the heat and work done on the system. When we do conservation of energy, remember when we lose energy, energy can be created or changed, changed, never created nor destroyed. So we go mechanical to thermal. It's very easy to take mechanical energy and convert to thermal. Think of it as a machine. What happens? You have friction. That's why you need all types of lubricants to prevent friction on machines to reduce heat, such as oil in your car or other things in machinery. But it is difficult to go from thermal to mechanical, the other way around. Heat engines, it's a device that's able to convert heat into mechanical energy continuously. A couple other points in our first law. Heat flows spontaneously from warm places to cold places. It takes energy to reverse this, so a refrigerator, where it's taking out warm and putting in cold. So it's moving the flow of cold air. So that's kind of the first law of thermodynamics, is the sum of work and heat is your total thermal energy added to a system. We talk about the second law of thermodynamics. Natural processes in our universe or in our world go so that entropy is increased. What is entropy? Disorder. Entropy is disorder. So natural processes go so the entropy is increased. All right, a couple other minor points from the second law. Predicts heat flow spontaneously from hot to cold, which we talked about. Energy in house is conversed by entropy increases. That's poorly worded. That's just kind of scratch that one. Don't worry about that one. And if no work is done on the system, entropy will peak. That's the second law of thermodynamics. The third law of the thermodynamics is the easiest one. Absolute zero, which is the temperature at which all motion ceases to exist, negative 457 Fahrenheit, can never be achieved. You can get negative 456.9999999, but you cannot achieve absolute zero, because if you did that, you'd violate multiple laws of physics at the same time. So absolute zero, the coldest temperature possible, can never be achieved. The three laws of thermodynamics, you'll kind of want to go over these. There'll be a couple test questions on these, some multiple choice, maybe a short answer on a couple things about thermodynamics, coupled in with a couple math equations that we learned. We'll review, and we'll have a test very shortly on chapters 11 and 12.